Hi, my name is Michaela Johnson,
Hi, my name is Nehemiah Smith.
and today we're going to be explaining Lewis-Dot structure, Vesper theory, molecular and ionic compounds. Okay, so with drawing the Lewis-Dot structure, you have to follow specific steps. So the first step is find the sum of the valence electrons in all the atoms. So hydrogen has one valence electron, and you would add, and carbon has 4, and nitrogen has 5. So 1 plus 4 plus 5 will give us 10 valence electrons. Okay. The second step is write the central atom, and the central atom is the least electronegative. So the central atom would be carbon, and then you would have hydrogen on one side and nitrogen on the other, and you would connect them both, and you use 2, 2, so you use 4 valence electrons, and you would do 10 minus 4, which gives us 6 remaining. So now you would fill the outer octets of the atoms, so hydrogen, carbon, nitrogen. Hydrogen only gets the 2 because it only has 1 electron. So you would fill nitrogen 1, 2, 3, 4, 5, 6. So 6 minus 6, which gives us 0. But now, not all of our atoms have filled octets because carbon only has 2 while nitrogen has 6. So we would move the 2 at the bottom and the 2 at the top to create a triple bond so that nitrogen and carbon are both balanced. And with the Vesper theory, this is the drawing. So we would look at our paper, and we would see which one is closest. So now we're going to talk about Vesper theory. So our Lewis-Dot structure, we're going to write it under. So now we have 2 bonded pairs, and we have 2 bonded pairs, and we have 0 non-bonded pairs. So that would show that our theory, our Vesper theory, would be linear. Okay, so for the molecular and ionic compounds, our example doesn't have any numbers next to it, so we would just write it as hydrogen, carbon, nitrogen.
Oh, that's so ugly.
Okay, so now I'm gonna do the next example. So I'm gonna show the way that I do it because that's what works best for me. Just gotta find what works best out for you. So you're gonna, like the first step, you're gonna find the valence electrons. So S equals 6, and then the oxygen also equals 6, and then we have this 3. So we would do 6 times 3, which is 18, and then we'll take this 6 and we'll add it, which will give us 24. Next step, you'll find the central atom, the least electronegative. So that is S. That's the one, that's the center. So you would do. Also, a key tip to figure out how many lines you're gonna have is right there. It's right there. That's how many lines you're gonna have. So we would do like that, and then oxygen will go right here. So we have 24, and I don't know if she mentioned in the previous question, but these lines are already worth 2. So we have 24 electrons to use. So 2, 4, 4, 6, and then 2, 4, 6, and then 2, 4, 6. Did I think I did it right? Okay. Subtract. And then we're subtract. So 2, 4, 6, 12, 17, 18.
19. 18, 19.
Oh, so we use 24 minus 24, which will give us 0. We don't have no more to use. Now we're gonna go to this one. So I do struggle with this one, so I'm gonna ask Kay to help me a little bit.
Okay. So now we have 3 bonded, and we have 0 non-bonded. And we would look at our paper, and this is planar. This is our Vesper theory for sodium trioxide.
Okay. And now for this one, to name it, we will look at the paper, and since it's 3, we will have. Oh, can you spell that?
SULFU.
And
Oxide.
and there you go.
Now we're going to do our third example. So carbon has 4 valence electrons plus hydrogen, which has 1, which is multiplied by 2. And we have bromine, which has 7 valence electrons, and then we times that by 2. And so we will do 1 times 2, which gives us 2, and then 7 times 2, which gives us 14, and then altogether this will give us 20. So we have 20 valence electrons, and now we have to find the least electronegative, and that is carbon. So carbon would be in the middle, and then we would draw 4 lines. Bromine, hydrogen. So each line is 2. 2, 4, 6, 8. Which gives us 12. 12. So now we have to fill in the outer atoms. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 0.
Okay. Now for this one, you will look at the paper, which we're gonna insert that so y'all can tell. But so we have 0. So isn't it? I think it's just linear because it's not.
We have 4 bonded pairs.
Right.
Yeah, right. So we will look at 4.
So isn't it this one? This one? Oh, I need to study this.
Now I'm going to explain wave and energy equations. The wave equation expresses the relationship of the speed of light to wavelength and frequency. So this is a short way of expressing the wave equation. We can write it out along by wavelength times frequency. Okay, so this equation is what Einstein used to explain the photoelectric effects. So H will be equal to 6.626 times 10 to the negative 34 joules.
Electron configuration. So important things you need to know is the number of sublevels and how many electrons each one have. So we have 4 sublevels, which is S, P, D, and F. S has 2 electrons, P has 6, D has 10, and F has 14. So for us to write electronic configurations, we would this is basically like a simple way to write it without having to write just a full number. So it's called simplifying it. So for example, we can look at carbon, for example, and carbon has 6 electrons. And if you don't know how to look for how many electrons they have, you just look at your periodic table, and on the left side of carbon, you would see the electron number. Actually, I'm gonna put it on this side so y'all can tell. So this is how it would look on the periodic table. So for us to write it, you will look, S is always first, as you can see. S is first, then P, then D, then F. So since carbon has 6 electrons, we would do 1s2. S only has 2 electrons, so you can only use 2. No other number, just 2. Then you would go again, 2s2, you can use 2. So we already have 4. We only need 2 more left. Then we will go to 2p. So 2p. Remember, p only has 6 electrons, but we don't need to use all 6 because we're already at 4. So we would use 2. And you can count 2, 4, 6, and that's the electronic configuration. Now let's do a bigger number. We can do neon. So Ne, and that has 10 electrons. So same form, different numbers probably. So 1s2, we already have 2. 2s2, that's 4. We need 6 more. P has 6 electrons, so we can use all 6 if we wanted to. So we would do 2p6, and that gives you 10, which is right here. And a last example we can use is, I'm trying to find a bigger number. We can use this one. I don't wanna, oh, we can use this one. GA31. I don't know how to pronounce that, but there it is. So this is a much bigger one. So we will probably go all the way to F if we need to. So bear with me because this is a big number, but 1s2, that's 2. 2s2, we at 4. 2p6, that is 10. And then, oh, you can look right here. This is the order you have to go in. That's the order. You can't skip nothing. You have to go in this exact order. So now we're done with the S, so 2p, we have to go to 3s now. So 3s, which is only 2. No matter what number is in front, we have to use this amount of electrons. S only has 2 electrons. So then after 3s, we'll go to 3p, which is, we can use another 6. So 12, 13, 14, 15, 16, 17, 18. We're at 18 electrons and we need 31. So after 3p is 4s. If you could already tell by the pattern what pattern we're going to. So that's 20, 18, 19, yeah, that's 20. Next is 3d. 3d has 10 electrons. So we need to count how many electrons we already have used. So 12, 13, 14, 15, 16, 17, 18, 19, 20. We're at 20. We could use 10, but that will only give us 20 and we need 31. So do we use the full 10? Ooh, actually we would not use the full 10. So 3D, so if you look right here, 3D, this is it. After 3D is 4P and that's 6. So actually we can use the full 10. So 10 and then 4P, which we will only use 2 and not the full 6. And there is our electronic configuration.
Next we're going to talk about electromagnetic radiation.
Yes, and we can see that through X-rays, colors in the rainbow, microwave ovens, and radio frequencies.
So this is the electromagnetic spectrum, and you can see at the bottom the wave frequency from gamma rays to radio frequency. It gets larger, so gamma rays is really, really small and really, really tight together. And as you move to the left, the waves start to get more bigger and more spaced out.
Yes, and electromagnetic radiation travel at the light of speed, which this is the equation, which is 3.00 times 108 m/s. The next topic we will explain is quantic numbers. I will explain the 4 quantic numbers and then we will find the complete set of quantic numbers for the valid electrons of a few examples. 4 quantic numbers that describe an electron is N, the principle of quantic numbers, the energy level, 1, 2, and 3, and so on. M with a symbol, I don't know how to pronounce it, and that's the magnetic quantic number. The orbital orientation, which range from negative symbol to positive symbol. There's also another symbol that I forgot, which is the symbol. It's the angular momentum, and that's the orbital shape. So S equals 0, P equals 1, D equals 2, and F equals 3. And then we have MS, the spin. The quantic numbers, that goes from positive 1/2 or negative 1/2. The rules are ON1, M equals negative or negative positive, MS equals positive or negative. Now on to some examples. So oxygen, we first find the valent electrons, which is 8, And then we write the electronic configuration, which is 1s2, 2s2, 2p4. The valence electrons are in the 4s and 2p, so n equals 2 equals 1. The values are -1, 0, plus 2. So the quantic numbers are 2, 1, -1, plus 1/2, 2, 1, 0, plus 1/2, 2, 1, plus 1, plus 1/2, 2, 1, -1, -1/2. The next example is helium, and helium has 2 valence electrons, so the electronic configuration for that is 1s2. The valence electrons are in the 1s orbital, so n equals 1 equals 0 s orbitals, 1 ms equals plus, the other ms equals negative, and the quantum numbers for that is 1, 0, 0, plus 1/2, and 1, 0, 0, -1/2. Yeah, sodium has 11 valence electrons, so the electronic configuration is 1s2, 2s2, 2p6, 3s1. It ends in 3s1, so n equals 3 equals 0, m equals 0, so the quantic number is 3, 0, 0, plus 1/2.